When you saw it, what was the extent of your reaction? Part 3 is an episode of the Degrees of Freedom Project, videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. This video and the two that preceded it, When You Saw It, What Was the Extent of Your Reactions, Parts 1, 2, and 3, address chemical reactors as modeled with the extent of reaction and fractional conversion. Moles are not conserved in chemical reactions. As a brief summary of Part 2, we did an example of a faulty propane combustor. The problem statement was that 2 kilomoles per second of propane are burned in 25% excess oxygen in a faulty combustor. 100% of the hydrogen combusts to form water, but only 80% of the carbon combusts completely to carbon dioxide. The remainder combusts to carbon monoxide. A. Calculate the molar flow rate of oxygen into the combustor. B. Calculate the molar flow rates of each of the combustion products. C. Calculate the total molar flow rate of the exhaust. The results were, the input oxygen flow rate was 12.5 kilomoles per second. The output flows were carbon dioxide 4.8 kilomoles per second, carbon monoxide 1.2 kilomoles per second, oxygen 3.1 kilomoles per second, and water 8 kilomoles per second. The total exhaust flow was 17.1 kilomoles per second. When there are multiple reactions in a process, the desired product, R, will not be the only one produced. To characterize how good the reactor is at producing R, there are two measures, yield and selectivity, that are used. Yield is how much of the limiting reactant actually goes to the desired product. To calculate the yield, we need to know how much of the limiting reactant could be converted into the desired product. We call this the possible moles or molar flow rate of the product. We then take the ratio of the moles or molar flow rate of the actual product to the possible product to calculate the yield. Selectivity is the ratio of the actual moles or molar flow rate of the desired product to the sum of all the undesired products. The goal in a reactor is almost always high selectivity, and usually high yield. However, if low fractional conversion of the reactant and hence low yield of the product results in high selectivity, we can use recycle to increase the overall yield of the product. See the Recycling Before Recycling Was Cool video for further details. Let's do yield and selectivity calculations for the propane combustor example. While both carbon dioxide and carbon monoxide are considered undesirable products of combustion reactions these days, carbon dioxide has the advantage that it is not extremely toxic like carbon monoxide is. Let's call CO2 the desired product and CO the undesired product of the propane combustion. We ignore the water because it is an unavoidable byproduct and can be separated from the exhaust gases relatively easily. For the yield, we'll take the ratio of the actual CO2 produced to the possible CO2. The possible CO2 is calculated by multiplying the propane feed rate by the ratio of the CO2 stoichiometric coefficient to the negative of the propane stoichiometric coefficient. We get 3 over the negative of -1 times 2 kilomoles per second, or 6 kilomoles per second. The actual CO2 flow rate from the example is 4.8 kilomoles per second. The yield is the ratio of 4.8 over 6, giving 0.8 or 80%. We could have gotten the same value from the problem statement. We will calculate the selectivity as the ratio of the desired product, CO2, to the undesired product, CO. From the example problem, that's 4.8 over 1.2, or 4. If there had been other carbon-containing products, we would have included them in the denominator, but we don't include the water for the reasons I've already addressed. At this point, students have a real tendency to confuse mole fraction, split fraction, and fractional conversion, because they all have the word fraction in them. When reading the problem statement, remember the following distinctions. Mole fraction is also called composition. For example, the stream has a mole fraction of 30% oxygen, or the composition of the stream is 30% oxygen. It is the moles or molar flow of the given species divided by the total number of moles, or total molar flow rate. It is typically specified or calculated for a stream. Split fraction only refers to separators. It is the fraction of a species being fed to the separator that comes out in a specified stream. For example, the split fraction of species A with respect to stream 1 is 30%, or 30% of the A fed to the separator exits in stream 1. Fractional conversion refers only to a reactor or an overall process containing a reactor. It is the fraction of a fed reactant that is converted or reacted away in a reactor. For example, the fractional conversion of ethane is 30%. Or 30% of the fed ethane is converted in the reactor. The takeaways from this video are 1. For reactors with multiple reactions occurring, there is often one desired reaction product and one or more undesired reaction products. 2. The yield is the fraction of the desired product that could be produced that is actually produced. The goal is usually, but not always, high yield. 3. The selectivity is the ratio of the desired product to the undesired products. The goal is usually high selectivity. 4. Don't confuse mole fraction, split fraction, and fractional conversion. Thanks for watching. This video is brought to you by the DOFPro team.